So, Newtonian physics, applied to the observations of Hubble, gives us a pretty good description of our universe, and many things agree. At the end of the day, when you want to look very far away or deep into the past, when we are trying to determine whether omega is bigger than 1 or less than 1, we are dealing with objects that are distances comparable to the inverse Hubble time, the Hubble time times the speed of light. So objects, by definition, that are not very near to us, and that means that their recessional speed in our little Newtonian model is not negligible compared to the speed of light, which means that relativity is important. So we have worked with Newtonian physics to get some intuition, and now we have to address the question of how to describe an isotropic, homogeneous, time-dependent universe in the context of the general theory of relativity. And this is a subject that was first addressed by a Russian physicist called Friedman in the 1920s, not long after Einstein published his theory of relativity. It turns out that making assumptions like isotropic and homogeneous simplifies the equations of general relativity very much, and so it was possible. It was one of the earliest solutions that were found. The earliest classes of solutions that were found to Einstein's equations were in fact the space-times in which space is described by space that is isotropic and homogeneous. In other words, at every point looks exactly the same as at every other point and has no preferred directions. Now, a space-time of this form has several simplifying properties. The first is that we can indeed think of it as a sequence of the same space, essentially. We'll see exactly to what extent we mean the same space at each time. So there are no changes in the structure, no qualitative changes in the structure of space over time. Second, there is a notion of time. When we talk relativistically about the behavior of space as a function of time, you have to be very suspicious, because we're talking about observers in distant places in the universe. How can they have the same time? Well, we will see that there is, in a relativistic sense, a notion of time that is valid everywhere. Everywhere in the universe. It is the proper time of a certain class of observers that you can generate in this universe. And as these observers measure the universe, they will find that each of them, every one of the observers, no matter where they are, if they belong to this special class, we'll call them co-moving observers, and we'll talk about who they are. Each of those co-moving observers will find at any point in the universe a universe that is isotropic and homogeneous, and in fact will describe exactly the same universe. Again, this is a universe that is actually homogeneous, so it has no galaxies or clusters in it. Those we will treat later as small perturbations on the general structure. So, what does general relativity tell us? Well, in general relativity, what that means, one of the properties, remember now, the shape of space and time is responding or encoding the gravitational influence of matter. Matter is distributed homogeneously everywhere. That is the assumption, because that is what causes gravity to be homogeneous, the same everywhere. Remember that the geometrical implementation in relativity of gravitation is the curvature of space and time. So the curvature of space-time is the same everywhere. And in particular, when we restrict to the what I call space at any given one time, that space is going to be a space that itself is homogeneous and isotropic, so every point in space looks exactly the same. And I can find what that means is in particular that the curvature, if this space is curved, its curvature is the same everywhere. So it turns out that you're led to describing the space in which we live as a space which has the same curvature everywhere, and this turns out to be a very simple problem in geometry. And what we have drawn here on the right-hand side is a collection of two-dimensional spaces whose curvature is the same everywhere. So this is a classification complete of all two-dimensional spaces. So I'm talking where I draw this ball, not of the ball, but only of its outside, of spaces that look everywhere the same. The bottom example is the familiar Euclidean plane. It is certainly a property of the plane, if infinite, that it looks the same everywhere. It is also a property of a sphere that if you rotate it around, any point can be interpreted as the North Pole, and unless the sphere is rotating, nobody knows There's nothing special about the north pole of a sphere. On Earth, it is the rotation that picks a particular pole. And so every point on a sphere looks the same. And this saddle-shaped thing, if you complete it on the bottom, is this surface of negative curvature that I showed you when we talked about general relativity. And it too, for reasons that are less obvious, has neither a preferred direction nor is there a difference. You can sort of slide it around so any point looks like any other point. But these are all the two-dimensional spaces, and it turns out that all the three-dimensional spaces of constant curvature are essentially three-dimensional analogs of these. So the analog of the plane is just plain old-fashioned Newtonian, Euclidean, flat three-dimensional space. The analog of the sphere, which we call a surface of positive curvature, is basically the three-sphere. So if you imagine a ball in 4 dimensions, the 4-dimensional ball, then the outside of that would be a three-sphere, just as this two-dimensional surface is the outside of a three-dimensional ball. And then you can make a slightly more complicated construction of the hyperboloid, which is a surface of constant negative curvature. Now, what does curvature tell us? Well, curvature tells us, as we said, about the behavior of geodesics, straight lines in this space. Remember, these are not space-time geodesics. These are straight lines in space at a given time. And it's not completely clear, but of course geodesics on the plane are just straight lines. Geodesics, as we saw, on a hyperboloid diverge, and geodesics on a sphere, as we are familiar with, converge. We talked about this when we talked about general relativity and geometry. And one way to measure this is that if you draw a triangle on the plane, then the sum of its angles is 180 degrees. If you draw a triangle on the hyperboloid, the sum of its angles, as you can see, is less than 180 degrees because the straight lines diverge, and the sum of the angles of a triangle on the sphere is larger than 180 degrees. Of course, the larger the triangle, the more the deviation. Very small triangles on a sphere, well, very small chunk of anything, looks flat, remember? And so a very small triangle has a sum of the angles very close to 180. The deviation is measured by the area of the triangle. In other words, what fraction the triangle occupies, in this case, of the entire sphere. So there is a something with the dimensions of area, which we'll call R0, of inverse area, that measures the total curvature, and so that measures the curvature of the object. In the case of the plane, the curvature is 0, so all triangles sum to 180. In the case of hyperboloid, there is a negative number minus R0, and the sum of the angles of any triangle is 180 minus its area times R0, and here it's 180 plus the area of the triangle times R0. So what does this A say? Well, of course, if you have a two-dimensional sphere, there are many two-dimensional spheres. They're not all exactly the same. Well, you can move the sphere around, but remember, when we're talking about the sphere, I draw two-dimensional surfaces as curved surfaces because they sit inside flat three-dimensional space, which is all that my little brain can handle. Certainly my graphic skills. And so, but really I'm thinking of the two-sphere as itself. There is no inside or outside, or in our case, if our universe is a three-sphere, it's just the three-dimensional sphere. But the three-dimensional, so moving it is meaningless, but there are three-dimensional spheres with different volumes, or two-dimensional spheres with different sizes and areas. And so what I'm saying here is that I can take the same sphere and make it bigger or smaller, and if I keep a constant size triangle on it, the sum of the angles of the triangle on a big sphere will be closer to 180 than the same triangle on a little sphere. And because R has dimensions of area, if you double the radius of the sphere, the area that I'm talking about will go as the square of the size of things. And note that this is a property of area even when you're talking, this is not because I'm in 2 dimensions, this too is not the dimensionality of space, it is the fact that the deviation from 180 degrees is captured by the area of a triangle, which makes sense even if the triangle is drawn in 3 dimensions, though in principle in 3 dimensions you could have a space where a triangle drawn this way has a different deviation from 180 than a triangle drawn that way or a triangle drawn that way. That would be a space that is not isotropic. In an isotropic space, it doesn't matter which way you draw the triangle. The only property that determines how its angles add up is its area. So there's just this one number, R0, that tells you how bad the deviation from flatness is. So we parameterize these 3 solutions as k times R0 over a squared, where k equals +1 for a surface of positive curvature, k equals -1 for a surface of negative curvature, and k equals 0 for a flat universe, in which case R0 can be whatever you want because it's multiplying 0. And I described some properties of these three spaces here. I said that a surface of constant curvature and a space, a three-dimensional space of constant positive curvature, is closed. It's finite in the sense that just as on the two-sphere, you cannot get as far as you wish from a given point. If you go far enough in any direction, you will come back to where you were. This is also true on the three-dimensional sphere. There's a limit to how far two observers can be. We know that if we live on a positively curved finite universe, then it's very large because we have not seen the backs of our heads, or the backs of our heads as they would have been billions of years ago. So the farthest place we can see is not yet us, but for all we know, it could be that if we looked, a trillion light years away, then we would be looking at this place long ago in the past. The hyperboloid is open. In other words, there are observers that are arbitrarily far from each other, so we call that an open space. And the flat Euclidean plane, just as flat three-dimensional space, is open in the sense that you can go to infinity. We might have a opportunity to discuss why I put a question mark here later on. So Friedman tells us that if our space is isotropic and homogeneous, it's one of these three. And as it grows, we can characterize expansion by fixing a value for R0, say the curvature now, the deviation from 180 degrees in today's space, and then letting A just be the scale factor. As distances grow, the space becomes closer to flat. That is true at any given scale in all of these spaces. So, what else is true about the geometry of these spaces? Well, first, space is of course homogeneous. This scale factor, A of t, describes the distance between those observers for whom the curvature is constant, those observers that see a homogeneous universe. Who are those observers? Well, it turns out that all of these observers, we can pick co-moving observers that see an isotropic universe, who are all inertial. Oh, that's great. We know who the inertial observers in our universe are. We are. Everybody sitting on some galaxy somewhere is an inertial observer because all galaxies are in free fall. In our dust universe, every flake of dust could be thought of as an inertial, co-moving observer because none of them had peculiar motions. They all saw an isotropic universe. And the proper time of these observers is the time that we will use, and they all agree on it because homogeneity means they all see the same thing. And so if they all start their time at some point or use the redshifted blackbody spectrum of the cosmic microwave background to calibrate their clocks, they will all compute. I'm not saying that people on some galaxy measure time in the same Babylonian-inspired hours that we do. All I'm saying is that if you define a physically meaningful definition of time, it will move the same here and on a galaxy far, far away because the universe is homogeneous. And therefore, we do have a global notion of time for all these co-moving observers, of which, sitting on any dust flake in the dust world, you are one. And indeed, the distance between two observers scales with time, just as the uniform expansion that we saw determines it. And again, we pick a time t0, which if you want, we can set to 0, and say that the scale factor now is 1, and then scaling away, multiplying by a. So the entire history, the entire all properties of this universe are given by essentially two numbers, R0, the curvature today, and the function A of t, which describes its evolution. Now, in all of these universes, remember, I drew a picture of space, and you can draw straight lines on space, but what moves along these straightest lines in space? You will remember that when I drew the space around a black hole, I mentioned that actually objects do not move around straight lines in space. That is true, but in homogeneous spaces they do. And in particular, light moves along geodesics of space, or along those straightest lines. If you draw a triangle with laser beams in our universe, those laser beams follow geodesics of the possibly curved space that we live on. And they move, of course, as measured by any observer, with speed c. This is not something I have to tell you. This is a property of relativity, so we expected that. But the fact that light moves along geodesics is a property of homogeneous it always moves along a space-time geodesic. The fact that the trajectory in space over time is a geodesic is a property of homogeneous spaces. And you can solve Maxwell's equations in the presence of relativity, and you find that, as we have already foreshadowed, light that is emitted at time t emission with a wavelength lambda emission will be observed at a later time at a longer wavelength, and the ratio of the wavelengths is precisely given by the ratio of the scale factors, which, remember, determine the changes in physical distances between things and the way in which curvature is diluted. It turns out that this also determines, just as we foreshadowed, the stretching of the wavelength of electromagnetic radiation. This you get by solving Maxwell's equations coupled to general relativity, something I don't plan to do, but it's a fact. Notice this is not a Doppler event. Both of our observers, to the extent that it's possible to be at rest in a changing universe, are co-moving. In other words, they're sitting on the dust. Their only motion is their participation in the overall uniform expansion. And it's a little bit different from the typical gravitational redshift. So is this a gravitational redshift? Well, the answer is sort of yes, in the sense that it is generated by interaction with gravity. But it's strange because in the gravitational experiment of Pound and Rebka, we saw that light emitted from the bottom floor to the top floor was redshifted, and light emitted from the top to the bottom floor was blue shifted. Here, there is no gravitational blue shift because no matter which direction, if A observes B, then A observes B's past. Therefore, the time of emission at B is always earlier than the time of observation at A. Conversely, if B observes A, then again, B is observing A's past. It's because photons always move into the future that they're always redshifted. In that sense, it's symmetric. In some sense, in a universe that is expanding, unless the universe is contracting, then all photons, if we have a crunch universe, then all photons will be blue shifted. But in a universe that is expanding, moving into the future is like moving uphill. Roughly, the dilution of matter makes a direction into the future in which a photon is moving out of a gravitational well. All photons move out of a gravitational well. All photons are redshifted. In an expanding universe, all photons are blue shifted in the contraction phase, if there is one. And again, we can use this property that light moves along geodesics, means we can draw the straight lines along which we observe stars and so on, and measure the angles between them. As we will see later, if you find all of this curvature of space confusing, don't worry too much. We have very good reason to believe that, in fact, our space is flat. It is not curved. This does not mean that our space is exactly flat. Of course, it's not flat. Our space is curved because superposed, say, on here are galaxy clusters and black holes and all kinds of wiggles. But if you average, if you look from very far away, our space is almost exactly flat. I will tell you later how we know this. But if you allow me to assume that is true, then we can use, again, the distance between things now is going to be, remember, we're going to measure the coordinates of positions of things in terms of which co-moving observer you are at. So each galaxy has a name, x equals 3, x equals 4, y equals 7. That's some grain of dust. And as that grain of dust moves, the distance between grains of dust with the same coordinates, the distance between the grain of dust at x equals 1 and at x equals 2 grows with the expansion of the universe. But we can determine to label the distance to every observer by the distance now. Can you measure the distance now? Well, you can't lay meter sticks, but you can pick coordinates. You can imagine I can measure the distance now to a nearby observer, and he can measure the distance now to a nearby observer. And other than the fact that it would take a long time to transmit the information, you can imagine, in principle, making that calculation, adding up all the small distances. That defines what we call d0. It's very hard to measure d0, the distance now, but there are things over large distances. But there are things we can measure. We can, for example, measure the distance from a small angle formula. If we have a galaxy of whose size we have an estimate, we can measure its angular size and compute an angular distance. And in a Robertson-Walker general relativistic sense, this is related to the coordinate distance now by this, by now, very familiar formula. Objects in the past are indeed smaller than they appear in the relativistic version of the expanding universe, just as we found for dust world, which is why we proceeded with it. You can also define a luminosity distance, the one for which the relation between brightness and luminosity holds, and the luminosity distance is given by exactly the same expression we found in dust world. That's why we worked on it there. We find that it still holds here. And again, the blackbody spectrum is redshifted, and that produces a redshifted blackbody spectrum with the expected ratios of temperature. So everything we did in dust world, or much of what we did in dust world, carries over to this case. What else does general relativity tell us? Well, like in the case of gravitational redshift, this tells us, as we said when we were computing luminosities, clocks in the past, as we observe events farther and farther into the past, clocks are observed to run slow because, of course, the clocks are synchronized with the fluctuations of electromagnetic fields. If we see redshifted photons, we see slowed clocks. We can use an atomic transition to define a clock. That's how we measure time, actually. And so this is just a statement that physics is consistent. It's also true that if you plot how fast light moves, of course light moves at the speed of light, but that doesn't mean that it moves at the speed of light in our coordinates, because remember, our coordinates are relative to observers who are tied to observers. X equals 3 is a particular flake of dust that is moving away from all other flakes, and so the speed in these coordinates with which light moves is slowed down as the universe expands, though all this is the statement that a given coordinate distance from x equals 1 to x equals 3 turns into more and more physical distance as the universe expands, while light moves at the same physical speed c. So this is not that shocking again. And massive freely falling objects still move along geodesics of space, so that's good. So if you set things into orbit, they will continue to be moving along geodesics of the big space modified by the local geometry. But their peculiar velocity, not of orbiting objects, but if you imagine that dust that we filled dust world with initially had some random thermal motions, not because there was some orbit going on, but just because we didn't set the dust started at rest, you will find that peculiar velocities are actually diminished over time as the universe expands. In other words, that's not too surprising. If those peculiar velocities were thermal, this would tell us that as the universe expands, it cools. And as we will see, this is true of the relevant thermal distribution, the blackbody distribution of photons. We already know that cools. Well, the temperature is proportional to the inverse of the redshift. We'll see how this applies, if we need to gases that are not gases of photons. And so this is, again, the analog of the first discussion of dust world, the kinematics, the description of dust world. In dust world, we then applied Newtonian gravity to find the time evolution, how the scale factor what behaved in time was determined by Newtonian gravity. The analog here is take all this data, specialize Einstein's equations to these simple homogeneous isotropic spaces with either positive, zero, or negative curvature, and find the evolution of the scale factor in those cases, and we'll turn to that in a moment, and that the analog of Newton's equation is Einstein's equation, which means we won't actually solve it, but I'll present the solutions.